We often use the Drake equation to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. It's a mathematical framework that forces us to multiply the rate of star formation by the fraction of those stars with planetary systems, and eventually the fraction that actually develop life. But to calculate that biological viability, we have to look past the planets themselves. Every rocky world requires heavy elements to accrete in the first place. To understand where those building blocks come from, we must trace galactic chemical enrichment back to the deaths of the most extreme stars. Intuition suggests a star with a massive supply of hydrogen fuel would burn for a remarkably long time. More fuel should equal a longer life. Astrophysics presents a paradox. The most massive stars in the universe, those with the largest fuel reserves, actually possess the shortest lifespans. This happens because a massive star's core is under extreme gravitational compression. To resist that crushing inward force and maintain hydrostatic equilibrium, the core must run its nuclear fusion reactions at a violently accelerated rate, tearing through its massive hydrogen supply. The stars with the most fuel consume themselves in a cosmic blink of an eye, and as we will see, this rapid catastrophic demise generates the intense thermodynamic conditions required to forge the heavy elements necessary for life. This chart shows stellar lifespans mapped by mass. A modest one solar mass star like our Sun will steadily burn for about 10 billion years. A massive blue giant, 20 times the mass of the Sun, exhausts its entire life cycle in a mere 8 million years. The distinction lies in the core dynamics. In the smaller star, a gentle outward thermal pressure balances gravity. In the blue giant, a relentless inward pull forces the core to generate a ferocious outward push just to keep the star from collapsing. Once the initial hydrogen is depleted, the star's fusion timeline drastically accelerates. Hydrogen burning lasts millions of years, leaving behind helium. As gravity compresses the core further, temperatures spike, and helium fuses into carbon for hundreds of thousands of years. Carbon fuses into neon over a few centuries. Neon becomes oxygen in a year. Oxygen burns into silicon over a few months. By the time the star begins fusing silicon, the progression is nearly complete. The entire massive silicon core burns out in exactly one single day. Silicon fusion yields iron-56. Every previous stage released energy because the atomic products were more tightly bound than the reactants. Iron-56, however, represents the absolute peak of binding energy per nucleon. You cannot extract energy by fusing iron. It is an endothermic reaction. It absorbs energy from its surroundings rather than radiating it outward. The outward thermal pressure that sustained the star for millions of years simply shuts off. In an instant, the cosmic tug-of-war ends, and gravity claims its total, crushing victory. As the dying shell continues dumping iron onto the dead core, it rapidly approaches a critical mass of 1.4 times the mass of the Sun. This is the Chandrasekhar limit, the exact threshold where electron degeneracy pressure fails to hold the mass up. A core the size of a small planet implodes to an object just 12 miles across in a fraction of a second. It collapses at nearly a quarter of the speed of light, generating temperatures exceeding 100 billion degrees, hot enough to shatter the carefully constructed iron nuclei back into raw protons and neutrons. Under this staggering pressure, the star undergoes inverse beta decay, or electron capture. Electrons are violently squeezed directly into protons. This forced merging converts the core into a dense ball of trillions upon trillions of neutrons, simultaneously releasing an overwhelming flood of nearly massless particles called neutrinos. The inner core rebounds, sending a shockwave outward through the still-in-falling outer layers. Initially, the shockwave stalls against the immense inward pressure, but that staggering flood of escaping neutrinos deposits exactly enough kinetic energy into the surrounding material to revive the shockwave and drive it outward. The result is a core collapse supernova. The entire outer structure of the massive star is blasted into the cosmos at 10% the speed of light, briefly outshining its host galaxy. Every atom of calcium in your bones and iron in your blood was forged in the core of a massive star and scattered by this specific violent explosion. Without the supernova, these heavy elements would remain forever locked in dead stellar cores, and rocky, habitable planets would never form. Behind the expanding debris, a highly compressed sphere remains, roughly 20 kilometers across, spinning hundreds of times per second, a neutron star. It survives under the Tolman-Oppenheimer-Volkoff limit. If its total mass exceeds 2.9 solar masses, it completely collapses into a black hole. To understand why it survives at all, we look to quantum mechanics. Subatomic particles are divided into two types: bosons, which easily share identical quantum states, and fermions, like neutrons, which absolutely cannot. The Pauli exclusion principle dictates that no two identical fermions can occupy the exact same quantum state in the same location. As gravity attempts to crush the core, the neutrons are forced into higher and higher energy states just to avoid duplicating one another. This resistance creates a powerful outward push, known as neutron degeneracy pressure. At the same time, the strong nuclear force behaves strangely at extreme compression. Below distances of 0.7 femtometers, the force that normally binds atomic nuclei together switches from attractive to intensely repulsive, pushing back hard against gravity. When we observe the physical structure supported by this standoff, we find distinct layers. Just beneath a whisper-thin atmosphere lies the outer crust. This layer forms a crystalline lattice of exotic, highly compressed, neutron-rich nuclei, surrounded by a sea of free electrons. It is immensely rigid, estimated to be 10 billion times stronger than steel, making it the strongest material known to exist in the universe. A neutron star is completely unlike a standard celestial body supported by heat. It requires no ongoing energy source. It is a macroscopic quantum laboratory, balancing perfectly on a knife edge between quantum mechanics and total gravitational collapse. Pushing deeper, you hit densities exceeding 400 billion grams per cubic centimeter, crossing into the inner crust. Here, nuclei become so bloated they can no longer contain extra neutrons. They literally leak out, floating freely in a phase called the neutron drip. These free neutrons pair up and begin to behave collectively, forming an exotic quantum state of matter, a zero-viscosity superfluid that flows with absolutely no friction. Lacking friction, the superfluid rotates independently of the solid crust, spinning via microscopic quantum vortices. When these vortices snag on the lattice and suddenly release their stored angular momentum, the entire star momentarily speeds up, an event we observe through telescopes as a pulsar glitch. Approaching the very base of the inner crust, the density climbs toward 100 trillion grams per cubic centimeter. At this depth, electromagnetic repulsion between protons perfectly rivals the strong force pulling the nucleons together. This tense equilibrium forces the matter to stretch and deform into strange, interwoven geometric shapes, sheets and tubes that physicists have termed nuclear pasta. Below the pasta layer, individual atomic nuclei dissolve completely as we enter the massive volume of the outer core. The outer core is a continuous quantum fluid. Here, neutrons flow as a frictionless superfluid, while the trace amounts of surviving protons pair up to form a superconductor, a material that conducts electricity with absolute zero resistance. A typical neutron star projects a magnetic field 1 trillion times stronger than Earth's. In the outer core, the superconducting protons confine this immense magnetic field into millions of narrow, quantized flux tubes that thread directly through the star's interior. Moving from the outer lattice, through the frictionless superfluid, past the pasta structures, and into a superconducting ocean, we see a highly stratified architecture that entirely defies the rules of classical thermodynamics. Finally, we reach the inner core. Densities here hit up to 10 times the density of a normal atomic nucleus. At this extreme limit, our well-tested models of nuclear physics fail entirely. Theoretical physics suggests that to avoid the massive energy cost of adding more neutrons to the densely packed core, the star might create entirely new particles. These are hyperons, exotic baryons that contain at least one heavy, strange quark. The appearance of hyperons gives the system new particle states to occupy. This relieves the intense degeneracy pressure pushing outward, creating what physicists call a softer equation of state. This creates the hyperon puzzle. A softer equation of state provides less pressure support against gravity, meaning a hyperon core should trigger a collapse into a black hole at much lower masses. Yet we routinely observe stable neutron stars weighing over 2 solar masses. To resolve this, we need empirical data capable of testing these core models. Since we cannot replicate these densities in a laboratory, we rely on gravitational wave observatories like LIGO. This chart shows the signal from GW 170817, recorded in August 2017. It tracks the gravitational waves emitted by two neutron stars spiraling toward a violent collision. In the final fraction of a second before they merged, the immense gravitational field of each star physically warped and stretched the crust of the other, raising massive tidal bulges on their surfaces. The exact degree to which a neutron star deforms depends strictly on its internal pressure, its equation of state. By measuring that tidal deformability in the gravitational wave signal, we can definitively rule out models of the core that are either too soft to hold up a massive star or too stiff to allow for the observed stretching. These strict gravitational constraints point to a moderately stiff equation of state, confirming that a standard mass neutron star packs its entire architecture into a precise radius of roughly 11 to 13 kilometers. The collision ended in a brilliant kilonova. The fading glow of radioactive debris confirmed that these extreme binary mergers are a primary production site for the universe's heaviest elements, like gold and platinum. The precise behavior of subatomic particles under immense pressure dictates how massive stars die, how they avoid total collapse, and how they shatter. It is these absolute extremes of physical limits that forge the heavy elements required for planetary accretion, ensuring that the variables of the Drake equation yield a biologically active galaxy.